Hello there, and welcome back to Black Hole Files, where curiosity drifts slowly like stardust, and yawning is practically encouraged. Whether you're wrapped up in blankets with your eyes closed, or just easing into your nighttime routine, I'm really glad you're here. Now, just a little warning. What you're about to hear might be a bit too interesting. I'll try to keep things calm and cozy, but if you end up staying awake, at least you'll drift off with a head full of strange wonders and cosmic truths. And while we settle in, where in the world are you listening from tonight? Somewhere rainy and quiet? Or maybe a city that never sleeps? Is it just past 10 and you're winding down? Or 3 a.m. and you've tried everything except counting stars? Feel free to share in comments. I always love knowing where these stories are reaching. All right, if you're all tucked in and ready, let's dim the lights on today and slip gently into the forgotten, the fascinating, and the far away. Now start with our first paradox. 1. Liar paradox. Statement: this sentence is false. Explanation: this classic self-referential paradox arises because if the sentence, "this sentence is false," is true, then it is asserting a falsehood about itself, a contradiction. Conversely, if it's false, then what it says is true, which again contradicts its initial assumption. The liar paradox illustrates a fundamental problem in truth assignment. A sentence that refers to its own truth value in a contradictory way has no consistent truth value. It can be neither simply true nor false. Variations include a person saying, "I am lying," or the question, "Is the answer to this question no?" All create a loop of self-contradiction with no resolution. Second, Epimenides' paradox. Statement: all Cretans are liars. Spoken by Epimenides, who was Cretan. Explanation: this is a historical variant of the liar paradox. Epimenides, a Cretan, claimed that all Cretans are liars. If we interpret liars as always lying, then if Epimenides' statement were true, it implies Epimenides, being a Cretan, must be lying, which would make the statement false. On the other hand, if the statement is false, then not all Cretans are liars, which could imply Epimenides might be telling the truth, making the statement true. This self-referential tangle is essentially the liar paradox in another guise. The Epimenides paradox highlights how even a seemingly simple declarative statement about a group, especially one that includes the speaker, can loop back and undermine itself. Third barber paradox. Statement: there is a barber who shaves all and only those men in town who do not shave themselves. Explanation: this puzzle, attributed to Bertrand Russell, asks, does the barber shave himself? If he does shave himself, then by definition he shouldn't, because he only shaves men who do not shave themselves. But if he does not shave himself, then by the rule he must shave himself, since he shaves those who don't shave themselves. This contradiction means no such barber can exist. The barber paradox is a more concrete illustration of Russell's set-theoretic paradox, the idea of the set of all sets that do not contain themselves, translated into a story about a barber. It shows how self-referential definitions can be logically inconsistent. 4. Russell's paradox. Statement: consider the set of all sets that do not contain themselves as members. Does this set contain itself. Explanation. This paradox, discovered by Bertrand Russell, revealed a fundamental inconsistency in naive. Set theory. If the set R summarizes all sets that are not members of themselves is considered, the question is whether R is a member of itself. If R is a member of itself, then by definition it should not be, because R contains only sets not containing themselves. If R is not a member of itself, then by definition it qualifies to be in R, so it should contain itself. Either assumption leads to a contradiction. Russell's paradox undermined Frege's naive set theory and led to the development of more rigorous axiomatic set theories. It highlights the dangers of unrestricted self-reference in set definitions. Fifth Curry's paradox. Statement. If this sentence is true, then Santa Claus exists. Explanation. Curry's paradox is a self-referential logical paradox that does not rely on negation. Consider the sentence. If this sentence is true, then Santa Claus exists. Suppose that statement is true. Then, since the antecedent, this sentence is true, holds, the consequent Santa Claus exists must follow, implying Santa Claus exists. If we suppose the sentence is false, then the implication, if sentence, then Santa exists, would be false. But in classical logic, an implication is false only when the antecedent is true, and consequent is false. Here, if the sentence were false, the antecedent, this sentence is true, is false, making the implication vacuously true, contradicting the assumption that the whole sentence is false. Thus, by self-reference and classical logic, the sentence seemingly proves an arbitrary statement. Santa Claus exists. Curry's paradox shows that in certain logical systems, self-referential statements can yield absurd conclusions without explicit contradiction, different from the liar paradox. Sixth knower paradox. Statement. This sentence is not known to be true. Explanation. The knower paradox arises in epistemology, the study of knowledge, by considering a sentence that says of itself that it is not known. If we call the sentence K is not known to be true. A paradox appears when we assume standard principles like A. If something is known, it must be true. Knowledge implies truth. And B. All truths are knowable. If K were true, then what K asserts is the case, meaning K is not known by anyone. But if K is a true statement that nobody knows, then it's an example of a truth that is unknowable, since knowing it would make it false. This conflicts with the idea that every truth is knowable. On the other hand, if K were false, then it is known to be true, but a false statement cannot be known to be true. Knowledge requires truth. Thus, either assumption about K leads to a problem. In short, the knower paradox shows an inconsistency in the naive combination of principles about truth and knowledge. It's closely related to Fitch's paradox of knowability and is basically a liar paradox, but in terms of knowledge rather than truth. 7. What the tortoise said to Achilles, Carroll's paradox. Statement. A dialogue in which Achilles tries to logically force a tortoise to accept a conclusion from premises, but the tortoise continually demands Achilles accept additional logical rules as further premises. Explanation. In Lewis Carroll's story, What the Tortoise Said to Achilles, the tortoise challenges Achilles to make him accept a logical inference. Achilles has a premise A. Things that are equal to the same are equal to each other. And premise B. The two sides of this triangle are things that are equal to the same. Aiming to conclude Z, the two sides of this triangle are equal to each other. The tortoise agrees to accept A and B, but refuses to accept that A and B logically entail Z unless Achilles presents that implication as an additional premise. When Achilles does so, premise C, if A and B are true, then Z is true. The tortoise then asks for a premise that includes the validity of C and so on ad infinitum. The paradox illustrates that no amount of adding premises will force someone to perform the act of logical inference if they refuse to do so. It highlights a philosophical problem. Logical inference cannot be reduced to additional premises. One must accept the logic itself, or reasoning never gets off the ground. This is sometimes called Carroll's paradox, not to be confused with a separate physics paradox of the same name. The lesson is that following a logical rule is not the same as adding another premise, or else an infinite regress results. 8. Pinocchio paradox. Statement: Pinocchio says, "My nose will be growing." Explanation: this whimsical paradox is a twist on the liar paradox, using the character Pinocchio, whose wooden nose grows whenever he tells a lie. If Pinocchio says, "My nose will be growing now," what happens? If the statement is true, then Pinocchio's nose will grow. But Pinocchio's nose grows only when he lies. And if his statement is true, he isn't lying, so his nose shouldn't grow. That would make the statement false. But if the statement is false, meaning Pinocchio's nose will not grow now, then Pinocchio just lied, which by the magic of the story would cause his nose to grow. That nose growth would make the statement true after all. Thus, Pinocchio's prediction about his nose leads to a paradox. His nose grows if and only if the statement is false, mirroring the liar paradox structure. This thought experiment shows that even a physical rule, nose grows when lying, combined with self-referential speech, can produce a logical paradox. 9. Berry paradox. Statement: the smallest positive integer not nameable in under 11 words. Explanation: this paradox arises from a self-referential description of a number, phrased differently. Define n as the least natural number that cannot be described in fewer than 11 words. The phrase in quotes is itself only 10 words long. Smallest positive integer not nameable in under 11 words, which seems to name that very number in 10 words. If the number n exists, then we have just described it in fewer words than supposedly possible. A contradiction. If no such number exists, i.e., every number can be named in fewer than 11 words, that also seems implausible, because there are infinitely many numbers and only finitely many short descriptions. The Berry paradox, attributed to G.G. Berry and discussed by Russell, exploits vagueness in the concept of nameable and the self-referential nature of defining something as the smallest undefinable. It reveals pitfalls in natural language and definition. Terms like nameable in under 11 words can lead to circular contradictions when applied to themselves. Desette-Kleinrosser paradox. Statement: a logical paradox arising in certain formal systems, like untyped lambda calculus, showing inconsistency via self-reference akin to Richard's paradox. Explanation: Alonzo Church and J.B. Rosser found this paradox in the 1930s while working with lambda calculus, a formal system underlying computation and logic. Without going into heavy technical detail, the Kleinrosser paradox constructs a self-referential expression in the untyped lambda calculus or in certain logical formalisms that leads to a contradiction. In essence, it's a formal analog of the liar paradox or Richard's paradox. It encodes a statement that says something like, "This formula does not have a proof within the system." The result is that the system becomes inconsistent. It can derive a contradiction. Specifically, by formulating an equivalent of Richard's paradox, one can show that in untyped lambda calculus, or naive set theory or certain logical systems, one can derive both a statement and its negation. The significance of the Kleene-Rosser paradox is historical. It demonstrated the inconsistency of a certain overly ambitious logical system, leading to restrictions in logic and type theory to avoid such paradoxes. For example, modern type theories avoid type contains itself scenarios to remain consistent. 11th grandfather paradox, time travel. Statement: a time traveler goes back and kills their own grandfather before the grandfather had any children. Thus, the traveler is never born. So, who killed the grandfather? Explanation: the grandfather paradox is a classic time travel causality dilemma. If you successfully prevent your own birth by altering the past, e.g., killing your grandfather in his youth, then you would not exist to travel back in time in the first place, so the deed could never have been done. But if the deed was never done, then your grandfather lives and you are born, which means you could travel back and kill him, leading to a logical contradiction in the timeline. This paradox illustrates the potential inconsistency of backwards time travel under a single history, classical timeline. It suggests that changing the past in a way that prevents the cause of the change leads to a logical impossibility, an inconsistency or loop with no self-consistent solution. Sci-fi and physics discussions have proposed various resolutions, such as the Novikov self-consistency principle, which would somehow prevent such paradoxical actions or outcomes from ever occurring. Or the idea of branching timelines. Killing your grandfather would create an alternate timeline where you were never born, separate from the original timeline in which you came. But within one timeline, the grandfather paradox remains a cautionary example of why time travel that alters the past seems to violate consistency. 12th, bootstrap paradox, ontological paradox. Statement: a time traveler or object is caught in a causal loop with no discernible origin. For example, a scientist from 2100 travels back to 1900 and hands a copy of a futuristic tech manual to someone who preserves it, and eventually it inspires the very scientist in 2100 to write that same tech manual. The manual has come into existence from nowhere. It's bootstrapped itself. Explanation: the bootstrap paradox involves an item or piece of information that is brought back in time and becomes the very cause of its own existence, creating a loop with no clear beginning. It's called bootstrap, from the expression pulling oneself up by one's bootstraps, implying something that is self-created. In such a scenario, an object or information has no origin. It wasn't created in the normal flow of time, but rather loops endlessly, e.g., a book or a piece of knowledge that time travels and completes a cycle. This is also known as an ontological paradox. Ontological, relating to existence. For instance, imagine a time traveler brings Beethoven's sheet music into the past and leaves it with the young Beethoven, who then composes those symphonies from the sheets. Who originally wrote the music? It seems to exist without an author, eternally looping. The bootstrap paradox doesn't necessarily involve a logical contradiction, unlike the grandfather paradox. Instead, it defies our normal notion of cause and effect and conservation of information. It poses the question, can information or objects exist without an origin, created from nothing? While weird, bootstrap paradoxes are self-consistent, but they feel deeply paradoxical because the origin of the information, matter, is inexplicable in linear time. 13th predestination paradox. Statement: a time traveler goes back in time to prevent some event, but by doing so, ends up causing the very event they tried to prevent. Explanation: in a predestination paradox, also known as a causal loop paradox, the time traveler's actions in the past are part of history all along, and they ultimately fulfill destiny rather than change it. An example: suppose a man travels back to discover the cause of a great fire. While in the past, he accidentally knocks over a lantern and starts the fire, the very fire that inspired him in the future to time travel in the first place. The paradox is that his attempt to change or investigate the past was itself the cause of the event. The events form a closed loop in time. Effect and cause chase each other. Predestination paradoxes often feel puzzling but are logically self-consistent. They show a scenario where free will might be an illusion, because any attempt to alter the past is already woven into history. Essentially, you cannot change the past in these scenarios. You end up fulfilling it. Many time travel stories use this to poignant effect. The act of trying to avert a prophecy brings it about, etc. In summary, the predestination paradox highlights how a time traveler's actions can be both caused by and the cause of a past event, locking them into a destiny they can't escape. 14th consistency paradox, temporal paradox. Statement: what happens if a time traveler does something in the past that prevents them from having ever time traveled in the first place? Explanation: this refers to the general paradox of violating causal consistency in time. It's essentially another way to frame things like the grandfather paradox. A consistency paradox arises whenever an action in the past would change history in a way that leads to a contradiction, specifically, that the action's cause is eliminated. For example, going back in time and accidentally preventing your own parents from meeting would remove the cause of you existing and thus of you time traveling. A contradiction. This is also called the temporal paradox or causality paradox. If time travel allows past alteration, any action that causes a logical inconsistency poses this paradox. In physics, one proposed resolution, Novikov's self-consistency principle, suggests that time travel might be possible only if events adjust to avoid any inconsistency, i.e., you might travel back, but something always prevents you from making a change that causes a paradox. Alternatively, some theories involve branching timelines, so you create a new timeline and thus avoid a paradox in the original timeline. The consistency paradox is basically a category that includes famous examples like the grandfather paradox. It emphasizes the apparent logical impossibility of a single timeline accommodating an event that would erase the cause of itself. 15. Newcomb's paradox. Statement: you are on a game show with two boxes. Box A always contains $1,000. Box B contains either under $1 million or $0, depending on a prediction the host has made about your choice. You have two options. Take both boxes or take only box B. A superintelligent predictor has already put $1 million in box B if, and only if, it predicted you would take only box B. If it predicted you would take both, box B is empty. What should you do? Explanation. Newcomb's paradox is a problem in decision theory and philosophy that pits two principles against each other. 1. The dominance principle. Taking both boxes yields $1,000 more, no matter what, so that seems better. And 2. The expected utility, prediction aspect. If you trust the predictor, taking only B likely nets $1 million, whereas both yields likely only $1,000. If the predictor is almost never wrong, one could reason that choosing only box B will result in $1 million, since the predictor would have foreseen your one-box choice and placed the million accordingly. Yet, once the boxes are set, from a purely causal perspective, the million is either there or not, and taking box A as well can't change that. So, why not also grab the guaranteed $1,000? This conflict creates a paradox in decision-making. To two box or one box. There is no consensus solution. It challenges our understanding of free will, causality, and rational choice. If one believes the predictor's decision is already made and cannot be affected, they may two box, get at most $1,000. If one believes their choice is evidence of what the prediction was, they may one box, and typically those who do so come away with $1 million in the scenarios where the predictor is highly reliable. Newcomb's paradox doesn't have a logical contradiction, but a philosophical conflict between two intuitions of rationality. It remains a famous thought experiment in decision theory. 16th causal loop paradox. Statement: a sequence of events forms a loop in time, where event A causes event B causes event C, and event Z causes event A again. Explanation: a causal loop, or closed time-like curve scenario, is inherent in many time travel paradoxes, especially predestination or bootstrap stories. It's called a paradox in the sense that it defies normal linear cause-effect intuition. The cause and effect chain is circular. For example, imagine a time traveler who goes back and gives a young engineer the plans for a time machine. That engineer grows up to build the time machine which the traveler eventually uses. Thus, the time machine's origin is a loop. There is no first cause for the information in the plans. It exists in perpetuity, uncreated. Such loops can be self-consistent, no contradictions, but raise the question of how the loop started in the first place. The paradox here is not a direct logical contradiction, but a puzzlement about origin and causation. Another example: you receive a mysterious note from the future telling you to do X, you do X, and later travel back to deliver the same note to your past self. The loop is complete. The note's information comes from nowhere outside the loop. Causal loop paradoxes often overlap with bootstrap paradoxes and predestination paradoxes. They challenge our understanding of causality, suggesting that the universe's timeline could perhaps be closed on itself in strange ways. While allowed in general relativity theoretically, if closed time-like curves exist, such loops make physicists uneasy because they seem to allow something from nothing, information or objects with no origin. Many believe some principle, like chronology protection, might forbid these in reality, precisely to avoid these weird situations. In summary, a causal loop paradox is the perplexity that arises when cause and effect form a closed cycle with no clear beginning. Paradoxes 11 to 16 above all deal with time travel and causality. Next, we move to paradoxes involving infinity, mathematics, probability, and so on. 17th, Zeno's paradoxes. Statement. Zeno of Elea proposed multiple paradoxes of motion. Two famous ones are Achilles and the tortoise, a fast runner. Achilles can never catch up to a slow tortoise with a head start because Achilles must first reach where the tortoise was, by which time the tortoise has moved a bit further, and so on ad infinitum. And the dichotomy, arrow. To travel a distance you must first go half, then half of the remainder, etc., which suggests an infinite number of steps. Explanation. Zeno's paradoxes question the continuity of space and time and the reality of motion. In Achilles and the tortoise, the reasoning is that Achilles must cover an infinite sequence of diminishing distances. How can he sum an infinite series of tasks in finite time? Similarly, in the dichotomy paradox, covering any distance involves an infinite series of halfway points, so motion seems impossible because one cannot complete infinitely many tasks in finite time. The arrow paradox argues that at any single instant an arrow in flight is motionless. So how does motion occur at all if time is a series of instants? The resolution, after millennia, comes from calculus. The infinite series of steps can sum to a finite limit. For example, 1/2 plus 1/4 plus 1/8 plus it's 1. In modern terms, Achilles does catch the tortoise because the time intervals get ever smaller and sum to a finite time. Zeno's paradoxes were profoundly important in prompting rigorous developments in mathematics, the concept of limits and convergent series, and in understanding that the intuition of infinitely many steps means infinite time was flawed. They highlight a difference between the mathematical abstraction of infinitely divisible tasks and the physical reality that motion is continuous and does not actually stop at each hypothetical division point. In summary, Zeno's paradoxes show that careful reasoning is needed when dealing with infinity. Motion is not paradoxical once we understand how an infinite process, like summing infinitely many fractions, can have a finite result. 18. Hilbert's Hotel. Statement. Imagine a hotel with infinitely many rooms, numbered 1, 2, 3, all of which are occupied. Can it still accommodate new guests? Explanation. Hilbert's Hotel is a thought experiment by mathematician David Hilbert, illustrating the strange properties of infinity. If a new guest arrives to a fully occupied, infinite hotel, it seems at first there's no room. However, the manager can ask each current guest to move from room N to room N plus 1. Shift each occupant 1 room up. Guest 1 moves to 2, guest 2 to 3, 3 to 4, and so on. Now room 1 becomes free for the new guest. In fact, even if a countably infinite number of new guests arrive, like a bus with infinitely many passengers, the hotel can accommodate them by moving each existing guest from room N to room 2N, thus freeing up all the odd-numbered rooms for the new guests. This scenario is paradoxical only in the sense that it defies finite intuition. An infinite set can be put in one-to-one correspondence with a proper subset of itself, something impossible for finite sets. Hilbert's hotel demonstrates that infinity obeys different arithmetic. For example, infinity plus 1 equals infinity in terms of cardinalities of infinite sets. It's not a logical contradiction, but a counterintuitive property. The hotel always has room, even when it's full, and can never really be full in the way a finite hotel can. This thought experiment helps one grasp the concept of different sizes of infinity, and how an infinite set can accommodate seemingly more elements without issue. It's a veridical paradox, true but surprising, of the infinite. 19th Banach-Tarski paradox. Statement: it is possible, mathematically, to take a solid ball, cut it into a finite number of pieces, then reassemble those pieces into two solid balls, each the size of the original. Explanation: the Banach-Tarski paradox is a result in set-theoretic geometry. It states that one can partition a 3D solid sphere into, say, 5 disjoint sets, then use rotations and translations to rearrange those pieces into 2 spheres of the same radius as the first. This defies physical intuition. It sounds like you're doubling volume out of nothing. The catch is that the pieces in the Banach-Tarski construction are highly pathological, non-measurable sets. Essentially, they are infinitely complicated. They're not ordinary chunks of matter you could cut with a knife. The paradox relies on the axiom of choice in set theory, to select points from the sphere in a certain way. So, while it's logically possible in mathematics, you can't perform it in the real physical world with actual objects, because real objects are made of atoms or continuous mass that obeys conservation laws. Nonetheless, it is mathematically consistent. It shows that in the realm of abstract infinite sets, volume, Lebesgue measure, doesn't behave nicely if you allow wild sets. You can decompose and reassemble sets in a way that creates or loses volume. This paradox is not a contradiction in mathematics. Rather, it's a startling theorem that highlights how our usual concepts, like volume, can break down under certain set-theoretic conditions. It's considered a paradox because the result, duplicating a sphere, is so counterintuitive. The Banach-Tarski paradox underscores the importance of measure theory and the fact that not all subsets of space have a well-defined volume if the axiom of choice is assumed. 20. Bertrand paradox, probability. Statement: if you pick a random chord in a circle, what is the probability that the chord is longer than the side of the inscribed equilateral triangle? Explanation: Bertrand's paradox reveals an ambiguity in the notion of a random chord. Depending on how you define the random selection process, you can get different answers, such as 1/3, 1/2, or 1/4. For instance, one way: pick 2 random points on the circumference and draw the chord. One finds probability 1/3 that it's longer than the triangle's side. Another way: pick a random radius and then a point on that radius for the midpoint of the chord. One gets 1/2. Another: pick a random point for the midpoint anywhere in the circle. Yields 1/4. Each method seems natural, yet they don't agree. The paradox teaches that When dealing with continuous infinities, the phrase "pick uniformly at random" can be ill-defined unless we specify the distribution. The resolution is that there is no single correct answer until the randomness is defined precisely. Bertrand's paradox highlights the importance of defining the sample space and probability measure in probability problems. Different interpretations lead to different results. It's a problem of indeterminacy rather than a contradiction. Once you fix a method, like random endpoints versus random midpoint, etc., the probability becomes well defined. The lesson is that not every question of geometric probability has a unique answer without additional assumptions. A cautionary tale in probability theory and a motivation for the principle of maximum ignorance, or other approaches to define a unique distribution. 21st Brace's paradox. Statement: adding an extra road to a traffic network can increase overall travel times for everyone, even if that road is free and direct. Explanation: Brace's paradox occurs in road networks, and more abstractly, in networks like the Internet, or even electric grids. Intuitively, one would think adding a new route or more capacity should never worsen traffic. But in some cases, drivers acting selfishly, choosing their optimal route, can lead to a worse equilibrium when an extra link is introduced. In a classic example, two congested roads connect start to end via two intermediate points. Adding a shortcut between those intermediate points can cause drivers to redistribute in a way that overloads parts of the network, making everyone's commute longer. Before the new road, traffic might split in an optimal way. After adding it, every driver might attempt to use what seems like a faster path. But collectively, these choices create additional congestion. The paradox is that removing that road could improve travel times. Brace's paradox demonstrates that in a system of self-interested agents, an intervention, like added capacity, can have counterintuitive effects on the equilibrium outcome. The broader insight, the optimum for the whole, social optimum, is not the same as the sum of individual optima, Nash equilibrium. A lesson from game theory and network flow. Brace's paradox has been observed in real road systems. Occasionally, closing a busy street improved overall traffic flow. In summary, more choices or capacity can sometimes hurt everyone if the system is not coordinated. A paradoxical outcome against naive expectations of monotonic improvement. 22. Gabriel's Horn, Painter's Paradox. Statement: Gabriel's horn is a geometric figure generated by rotating the curve y equals 1x for x greater than or equal to 1 around the x-axis. It is an infinitely long horn-like shape that has finite volume but infinite surface area. Explanation: this figure is also nicknamed the painter's paradox. If you tried to paint the inside of the horn, it seems you would need an infinite amount of paint, due to infinite surface area. But paradoxically, the horn can be filled with a finite volume of paint. Specifically, by using calculus, one finds the volume of the horn from x equals 1/2 is p, the units cubed, whereas the surface area is infinite. How is this possible? The resolution is that as x grows, the horn's radius shrinks to 0. Volume integrates radius squared, cross-sectional area, times length and converges, whereas surface area integrates radius, circumference, times length, and diverges. The paradox is a surprise that an object can enclose a finite three-dimensional volume, but have an infinite two-dimensional surface area. In practical terms, you could fill the horn with a finite amount of paint, but no finite amount of paint would suffice to coat its inner surface completely. As you go further in, the surface keeps stretching out, while volume contributions become negligible. This example challenges intuition about infinity. Different measures, area versus volume, can behave differently. It also underscores that finite versus infinite can depend on the dimensional aspect considered. Gabriel's horn is a classic example from calculus demonstrating the counterintuitive results of infinite processes in geometry. The term painter's paradox is often used for Gabriel's horn. The users list also mentioned a painter's paradox alternate, which likely refers to the same concept or similar infinite surface, finite volume scenario. 23rd Berry paradox, reentry. This paradox was already described as number 9 above. It appears again in some lists because it straddles categories of logical self-referential paradox and linguistic paradox. In summary, the Berry paradox arises from phrases like the smallest number not nameable in under 11 words, creating a self-referential contradiction. It demonstrates a problem with informal language definitions and has no resolution except to avoid such self-referential phrasing or to carefully formalize what nameable means. 24th Grandy's series. Statement. Consider the infinite series S equals 1 minus 1 plus 1 minus 1 plus 1 minus 1, 1 plus ad infinitum. What is S? Explanation. At first glance, grouping the terms in different ways gives different results. If you group 1-1 plus 1-1 plus dot, 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 each pair sums to 0, suggesting S equals 0. But if you stop the series at an odd number of terms, the partial sum is 1. If even number of terms, the partial sum is 0. The series does not converge to a single value in the usual sense. It oscillates between 1 and 0. However, a method known as Cesaro summation assigns it a value of 1/2. That is, if you look at the averages of partial sums, 1 plus 0, divided by 2 equals 0.5. 1 plus 0 plus 1 divided by 3 approximately equals 0.667. 1 plus 0 plus 1 plus 0 divided by 4 equals 0.5. These averages approach 0.5. This is paradoxical to intuition because it seems like, by algebraic trickery, you can prove 1-1 plus 1-1 plus equals 1/2. One popular manipulation is let S equals 1 minus 1 plus 1 minus 1 plus. Then 1 minus S equals 1 minus 1 plus 1 minus 1, 1 plus equals 1-1 plus 1-1 plus equals S, since subtracting the series from 1 yields the same series. So 1-S equals S, implying S equals 1/2. The paradox lies in the misuse of algebra on divergent series, something one must be careful about. Properly speaking, the series is divergent, no single sum. But under certain summation methods, like Cesaro, one can assign it the value 0.5. This result is used in some mathematics and physics contexts. The paradox shows that infinity and convergence can behave in ways that defy naive expectations. It reminds us that rearranging or summing divergent series is not valid. In standard arithmetic, Grandy's series is a classic example in the history of math that led to more rigorous definitions of convergence. 25th Skollem's paradox. Statement. Within standard set theory, Zermelo-Fraenkel with choice, it is proven that there are uncountable sets. For example, the set of real numbers is uncountably infinite. Yet, the Löwenheim-Skolem theorem implies there exists a countable model of set theory that satisfies the same statements, meaning in that model, uncountable sets exist. But the model itself is countable. Explanation. Skollem's paradox is a seeming contradiction between set theory and model theory. In plain terms, model theory's Löwenheim-Skolem theorem says that if a theory, like ZF set theory, has any infinite model, it has a countable model. So there is a countable model M of set theory in which, from inside the model's perspective, there are sets that M thinks are uncountable. But from an outside perspective, every element of M, including those uncountable sets of M, is actually one of a countable list, since M is countable. How can a set be uncountable in the model, but countable from outside? The resolution lies in the difference between internal and external viewpoints. Inside the model M, there is no bijection between that uncountable set and the naturals. M doesn't contain a function that pairs them off. So it's uncountable to M. Outside, we can see a bijection because we can list the model's elements. The paradox isn't a logical contradiction. It highlights that countable is relative to a model. A model can lack some bijections that exist externally. Essentially, what's countable or uncountable can depend on what functions exist in the model. Skollem's paradox underscores how a countable structure can satisfy statements claiming existence of uncountable sets, reminding us that first-order logic can't fully capture the semantic notion of countability. It's a milestone in understanding formal systems. Our intuitions from the outside don't directly carry in to all models of a theory. In short, there's no actual inconsistency in set theory. The paradox dissolves when carefully distinguishing between the perspective inside a model versus outside. 26. Richard's paradox. Statement. In English, we can catalog definitions of real numbers. For example, the real number with decimal expansion given by into an infinite list. Now define a new real number by a rule that ensures its decimal differs from the nth listed number in the nth decimal place. This new number, by construction, is not equal to any number in the list. But if every rule-based definition was on the list, how did we just define a new number not on the list? Explanation. Richard's paradox, named after Jules Richard, is akin to a semantic version of Cantor's diagonal argument and the Berry paradox. We start by assuming we have a comprehensive list of all definable real numbers in a certain language like English with finite descriptions. Using that list, we define a new real number by diagonalization, ensure its nth digit differs from the nth digit of the nth number on the list. This new number seems to have a definition. We just gave it. So it should have appeared on the list if the list was complete. But it clearly is constructed to differ from every listed number, a contradiction. The crux is the vagueness of definable and self-reference issues. The paradox exposes that the notion of all definable numbers is problematic in an ordinary language context. It leads to a self-referential definition that escapes the initial enumeration. It's similar to Cantor's proof that real numbers are uncountable. But here the twist is the definability in language. which is not formally precise without a specific logical system. Some resolutions note that there is no well-defined countable set of all English definitions because of Berry-like paradoxes. English, or any sufficiently rich language, can describe things that were meant to be outside its scope. In formal terms, Richard's paradox warns us that naive set, constructions involving semantic notions, like definable in English, can be inconsistent. It underlines the necessity for formalizing the concept of definability to avoid self-referential traps. Essentially, it is a semantic paradox, showing that our intuitive idea of listing all descriptions fails. There will always be a new description, like the diagonal one, not accounted for. 27th. Curry's paradox, re-entry. This paradox is the same as number 5 above, and it likely appears again in lists under logical paradoxes. Recap. Curry's paradox arises from a self-referential sentence of the form, if this sentence is true, then X, leading to the conclusion X, without requiring a direct contradiction. It highlights a problem in naive truth theories, or certain logical systems, where one can prove an arbitrary statement by self-reference. The solution typically involves restricting the logical system. For example, not allowing unrestricted self-referential truth predicates, or moving to non-classical logic, to avoid such paradoxical derivations. Next, we move to paradoxes involving probability, decision, and statistics. 28th. Chessboard paradox, Lloyd's paradox. Statement. Take a standard 8x8 chessboard, area 64 squares, and cut it into 4 pieces in a certain way. By rearranging those pieces, one can form a 5x13 rectangle, which appears to have area 65 squares, with 1 unit square hole. Where did the extra area come from? Explanation. This is a classic dissection puzzle paradox attributed to Sam Lloyd. The pieces are cut along. Lengths 2, 3, 5, 8, all Fibonacci numbers, and rearranged into a rectangle, apparently 5x13. The paradox is that 5 times 13 equals 65, one more square than the original 64. In reality, there is no extra area. The discrepancy arises from the fact that the pieces do not actually fit perfectly. In the 65 rectangle arrangement, the pieces don't align exactly. There is a very thin gap or an accumulated misalignment that amounts to 1 square of area, which is hard to spot by eye. In other words, what looks like a straight line forming the hypotenuse of the supposed triangle or rectangle is actually a very slight bent line. The paradox teaches a lesson in geometry. Figures that appear congruent or flush may not be, and a tiny difference, a fractional sliver of a unit along the hypotenuse, can add up to 1 whole unit of area. The missing square or extra square puzzle has multiple variants, all based on the same principle, a deceptive rearrangement due to non-identical slopes. It's a falsidical paradox. The result is false. You can't get 65 out of 64, and the error lies in an assumption that the pieces form a perfect rectangle. They do not. The illusion is achieved by distributing a 1 square area gap into many small, inconspicuous gaps. Once one measures carefully, one finds the long sides are not exactly straight. This paradox is a fun demonstration of how our visual assumption of continuity can be fooled. 29th coin rotation. Paradox. Statement. Roll 1 coin around another coin of the same size. By the time it has made one full revolution around the stationary coin, the moving coin will have spun around twice on its own axis, not once. Explanation. This surprising result often confuses people. If you imagine two identical coins on a table, one fixed and one rolling around it without slipping, when the moving coin returns to the starting point, the head on that coin, or any marked point, will have rotated 720 degrees relative to its starting orientation. The paradox is that many expect only a single rotation. After all, the rolling coin center went around once, matching the circumference distance of one circumference of the fixed coin, which equals one rotation. So, where does the extra turn come from? The resolution. The rolling coin effectively experiences two motions. One is the rotation due to the distance traveled, circumference. The second is an extra rotation due to revolving around the other coin. In simpler terms, when one coin rolls around another of equal size, it covers a path equal to one circumference, giving one spin. But also, it has been facing different directions around the circle, which adds another spin. A related everyday example is the Moon-Earth system. The Moon rotates once per orbit. It's tidally locked, so the same face points to Earth. But from an outside perspective, as it orbits the Earth, it actually spins on its axis once, meaning it shows the same face to Earth, but does complete a rotation relative to distant stars. In the coin scenario, the extra rotation can also be visualized by considering extreme cases. If the fixed coin were shrunk to a point, essentially rolling around a point, the moving coin clearly would spin once from the rolling distance. If the fixed coin has radius, the moving coin's center goes around a circle, and effectively that adds another full twist. Scientific American notes that many find it hard to accept and must try it physically. The coin rotation paradox is not a violation of any physics. It's a counterintuitive result of combining rotational and translational motion. It demonstrates how an object's orientation can change due to path curvature in addition to distance. The key is that the coin rotates relative to a fixed frame, both from rolling and from going around the circle's center. Thus, the coin's tally of spins is 2, not 1. 30. Kramer's paradox. Statement. In algebraic geometry, two distinct cubic curves, third-degree polynomial equations in two variables, can intersect in 9 points. However, there are formulas suggesting that two cubics should determine at most 3 by 3. 9 points, and by naive parameter, counting one might expect at most 8 points of intersection. So, how do we get 9? Explanation. Kramer's paradox from the 18th century pointed out a puzzling count. A general cubic curve is determined by 9 points, since it has 9 coefficients minus a scale factor. So one might think if two different cubics share 9 points, they would have to be the same curve, because 9 points fix a cubic. Yet, two distinct cubic curves can intersect in 9 points. The resolution lies in the special cases and degenerate scenarios. If two cubics intersect in 9 points, those points aren't arbitrary. They satisfy additional constraints that force the two curves to have some special relationship. In fact, there is a theorem that two cubics that meet in 9 points have an algebraic dependency. Essentially, there is a pencil family of cubics through those points. In general, two independent cubics would intersect in up to 3 times 3 equals 9 points by Bezout's theorem, but typically fewer because often some intersections are complex or at infinity or are countered with multiplicity. Cramer's paradox highlighted that just because two conditions, curves, can mathematically intersect in a number of solutions up to the product of degrees, specifying all intersection points freely can overconstrain the system. The subtlety is that the 9 points might force the two cubics into special alignment. In modern terms, the resolution uses projective geometry and Bezout's theorem more carefully. Two distinct cubic curves indeed intersect in exactly 9 points, counting multiplicity and including points at infinity. If all 9 intersection points are ordinary and finite, no multiplicities, that implies a special condition. Basically, those 9 points cause an entire one-parameter family of cubics, not just a unique cubic. Thus, two distinct cubics sharing 9 ordinary points is only possible if the 9 points are not in general position. They impose dependent conditions. Cramer's paradox was resolved by these deeper insights, showing that naive counting can mislead if we ignore degenerate cases or projective considerations. It teaches caution in using parameter counting arguments and foreshadowed the rigorous development of intersection theory. 31st, Girard's paradox. Statement: in certain type theory systems, like System U or early versions of Martin-Löf type theory, one can construct a self-referential type that leads to a contradiction, analogous to Russell's paradox. Explanation: Girard's paradox, discovered by Jean-Yves Girard, shows that if a type system is too permissive, specifically if it allows a type to be a member of itself, the so-called type-in-type, or impredicative polymorphism at the top level, then the system can express a paradox similar to Russell's set paradox. In simpler terms, imagine a type theory where we have a type of all types, including itself. One can encode something like the type of all types that do not contain themselves and derive a contradiction. Girard's paradox proved that System U, which had such an unrestrained universe of types, was inconsistent. The paradox is the type-theoretic analog of Russell's paradox in set theory. The significance is that it forced type theorists to introduce hierarchies, like type 0, type 1, etc., or more complex universe levels, to avoid such self-referential type definitions. In practical terms, a language or proof assistant must avoid a type containing itself to remain sound. Girard's paradox itself is a technical, logical result, not something one sees day to day, but it underpins the design of reliable logical systems. It underscores that allowing absolute self-reference in a formal logical system, be it sets or types, tends to cause inconsistency. Modern type theories circumvent this with stratification or other restrictions. So, Girard's paradox is a milestone illustrating the necessity of those restrictions, and it parallels the earlier paradoxes of naive set theory, confirming that type Monroe set of all sets is as paradoxical as Russell's original scenario. 32. Hausdorff paradox. Statement: on the surface of a sphere, like the surface of the Earth, it's possible to take a certain countable subset C of the sphere, such that if you remove C from the sphere, the remainder of the sphere can be partitioned into 3 pieces A, B, and D, where A and B are congruent by rotations to each other and to the entire remainder B, D of the sphere. Explanation. The Hausdorff paradox is a precursor to the Banach-Tarski paradox, but specifically for the two-dimensional case. Sphere, using the axiom of choice. It shows that if you exclude one point, like the North Pole and some orbit of rotations, to avoid trivial issues, you can paradoxically decompose the sphere. In simpler but loose terms, you can partition a sphere's surface, minus a small set, into a finite number of pieces that can be rotated to reassemble into one piece that seems larger than part of the original. Formally, Hausdorff found that assuming the axiom of choice, there's a paradoxical decomposition of the sphere S squared minus a countable set into congruent sets in a way that defies usual area measure. This was a stepping stone to Banach-Tarski, which is about three-dimensional volume. Hausdorff's paradox deals with two-dimensional surface and rotations group, so 3. It implies there is no finitely additive rotation invariant measure defined on all subsets of the sphere that treats single points as zero, because if there were, this decomposition would force 0 equals one sort of contradictions. The paradox is resolved by understanding it's a falsitical paradox from the viewpoint of measure theory. The pieces involved are non-measurable sets. You can't assign a sensible area to them. So, while the paradox stands in terms of set theory, it doesn't violate actual measurable geometry, because those pieces are infinitely fragmented. The Hausdorff paradox thus illustrates again the counterintuitive results of the axiom of choice in geometry. It's possible to duplicate area on a sphere with a clever partition. It underscores why you can't have a rotation invariant area measure defined everywhere. It would conflict with this. It's essentially the spherical version of Banach-Tarski's result. Weird, but mathematically consistent, provided you accept the constructions allowed by choice. 33rd Hilbert Bernays Paradox. Statement. In a formal theory that can represent its own reference mechanism, like naming expressions, one can construct a term H such that H equals the referent of H plus 1. This leads to a contradiction, since it implies a number equals one more than itself. Explanation. The Hilbert Bernays paradox, also called a paradox of reference, is a lesser-known logical paradox presented by David Hilbert and Paul Bernays. It arises when you have a naive semantics for reference denotation inside the theory. They considered a theory that can talk about the referent of terms. Suppose denotes the name of expression E. Then using a self-referential construction, they define an expression H that essentially says the referent of equals the referent of plus 1. If you try to resolve it, let the referent of be some number n. The theory then proves n equals n plus 1, which is impossible. In simpler terms, it's like a variant of the liar paradox, but about reference. It shows a contradiction when a term tries to denote something in terms of its own referent. The resolution is that a formal theory cannot allow an unrestricted self-referential use of a reference function, just like how naive truth predicates cause liar-type paradoxes. The Hilbert Bernays paradox demonstrates the need to restrict how a language can refer to its own expressions, for example, by a hierarchical approach or some type distinction. It went largely unnoticed for decades, but it's important in the philosophy of language and logic as it parallels the liar paradox in the realm of reference, name, and object relationships. In short, the paradox is, If every name has a referent, and you allow naming of any phrase, you can create a name whose referent definition is self-contradictory. It shows limits of a theory's ability to refer to itself and influenced work on avoiding such semantic paradoxes. 34. Hooper's paradox. Statement. By cutting a 10 by 3 rectangle into 4 pieces and rearranging them, one can apparently form an 8 by 4 rectangle with a 2 by 1 hole, suggesting area has changed from 30 to 32. Explanation. Hooper's paradox is another dissection illusion from the 18th century, attributed to William Hooper. You have a rectangle of area 30, which is dissected cleverly. After rearrangement, it seems to make a figure of area 32 minus a small gap, or vice versa, depending on the version. It's similar to the chessboard paradox or missing square puzzle. 28 above. In essence, the 4 pieces have been rotated and shifted such that the misalignment of edges accounts for the area discrepancy. There is no actual paradox in conservation of area. The extra 2 units of area are hidden in a slight gap along a slanted edge or an overlap, depending on the construction. The paradox exploits the eye's tendency to see the new shape as a perfect rectangle, when in fact it isn't. In Hooper's original presentation, a 10 by 3, area 30, is turned into a shape that looks like 8 by 4, area 32, with a hole, or in some versions, an apparent 7 by 4 rectangle, 28, plus an overlap, etc. The specific numbers can vary, but the principle is a dissection puzzle trick. Like the other vanishing area puzzles, it demonstrates that our assumption about straightness or alignment can be fooled. If you measure precisely, one piece's long edge is slightly angled, so the assembled rectangle isn't truly rectangular, and the small slivers add up to a whole unit or 2 of area difference. In summary, Hooper's paradox is a fun demonstration that geometry can play tricks. It's resolved by recognizing the very slight irregularities in the reassembled figure that our eyes or the diagram might not reveal readily. It's essentially the same phenomenon as the missing square puzzle, a falsitical paradox where the flaw is a subtle geometrical cheat. 35th. Interesting number. Paradox. Statement. All natural numbers might seem interesting in some way. Suppose there is a smallest natural number that is dull or uninteresting. That number itself becomes interesting for being the smallest uninteresting number, a contradiction. Explanation. This is a tongue-in-cheek paradox in recreational mathematics. We start by assuming the contrary. Not every number is interesting. There is a set of dull numbers. Since the natural numbers are well ordered, there would be a least dull number. Call it n. But the property of being the smallest uninteresting number is a rather interesting property. It's a number about which we can make a curious statement. Therefore, n isn't uninteresting after all. This contradiction suggests that our initial assumption that there are uninteresting numbers might be flawed. In reality, the paradox plays on a vague definition of interesting. What qualifies as interesting is subjective and not formally defined. So, logically, the argument is a bit tongue-in-cheek. Some call it a semi-paradox or a joke paradox. It does highlight a kind of self-referential loop. Uninteresting is defined in terms of lack of properties, yet the well-ordering of n forces an extremal property that bestows interest. The resolution is usually the term interesting cannot be rigorously defined in a way that makes the argument sound, it's inherently subjective or context-dependent. In practice, we can always find some trivial property for any given number if we try hard enough, like the first number not mentioned on this page until now, etc., blurring the line between interesting and uninteresting. The paradox often is used as a humorous way to say every number is interesting. Indeed, it's hard to find a number about which absolutely nothing of note can be said. So, the interest in number paradox is more of a curiosity about language and sets, rather than a strict logical paradox. It reminds us that self-referential definitions, the smallest uninteresting number, can produce circular outcomes. 36. Missing square puzzle. Triangle paradox. Statement. Cut a right triangular figure into a few pieces and rearrange them to form a very similar triangle, but with one square unit of area missing, a hole. How can moving the pieces create a hole? Explanation. This is the famous missing square puzzle, often attributed to magician Paul Curry, 1953. Typically, a 13 by 5 right triangle, hypotenuse, not truly straight, is dissected into 4 parts that can be rearranged into a 13 by 5 shape with a 1 by 1 hole. The paradox arises because both arrangements seem to form a 13 by 5 triangle, yet one has a missing square. In reality, the two triangles are not congruent. They have slightly different slopes on the hypotenuse. The difference is hard to see but crucial. In one arrangement, the overall shape bows outward slightly, and in the other, it bows inward, amounting to an area difference of exactly 1 unit. The key is that the pieces don't perfectly fit. There is a very thin parallelogram gap spread along the hypotenuse when the hole is not visible, or conversely, the pieces overlap slightly when the hole is visible. That tiny discrepancy sums to 1 unit of area over the length of the hypotenuse. Using coordinates or slopes, one triangle's hypotenuse has a slope of 2/5 equals 0.4. The other has 3/8 equals 0.375. These are not the same, so the assembled figures aren't true triangles. When overlaid, there's a slender sliver of area accounting for the missing square. Like the chessboard paradox, Sam Lloyd's, and Hooper's paradox, this is a falsitical paradox. It tricks our perception, but is resolved by precise geometry. The lesson: just because pieces seem to form a perfect larger shape doesn't mean they actually do. A small deformation can cause a big difference in area. The missing square puzzle is a classic demonstration in math classes of the need for careful reasoning about geometric equivalence and the pitfalls of assuming straightness or planarity from a diagram. 37th Painter's Paradox. Alternate. This seems to be referring to the same paradox as Gabriel's horn discussed in number 22, where an infinite surface exists despite finite volume. Recap: Gabriel's horn, the infinitely long horn with finite volume but infinite surface area, is sometimes dubbed the painter's paradox because it suggests you could fill the horn with paint, finite volume, but not have enough paint to coat its inside, infinite area. The resolution is that as the horn narrows, a finite volume of paint can fill it, but that paint layer would get thinner without bound. You simply can't maintain a non-zero thickness all the way. Hence, you can't truly paint it uniformly. The term might also apply generally to any scenario of finite measure in one sense and infinite in another. 38th, Parando's paradox. Statement: two losing strategies or games, when played in alternating sequence, can surprisingly produce a winning outcome. Explanation: Parando's paradox comes from game theory. Imagine game A and game B. Each, if played alone, makes you lose money in the long run, negative expected value. However, if you randomly alternate them or play them in a certain pattern, AA, BB, or AB, AB, etc., the combined sequence has a positive expected value. This counterintuitive result was discovered by J.M.R. Parando around 1996 in the context of flashing Brownian ratchets, and then framed as gambling games. A simple example: Game A might be a biased coin that loses a bit on average. Game B might be another coin whose bias depends on your current capital mod, some number, by itself. B also makes you lose on average, but by switching between them, the dependencies can interfere constructively, leading to gains. It's paradoxical because people assume that combining losing propositions shouldn't produce a winner, like two wrongs don't make a right. Yet here, due to nonlinearities or state-dependent effects, it can. The resolution of the paradox is recognizing that the games are not independent or linear. The alternation exploits the state dependence in a way that one game sets up favorable conditions for the other. The paradox has been demonstrated in various forms, including physical simulations and financial analogies. It has even been related to concepts in thermodynamics and evolution. The key insight: nonlinear or state-dependent systems can behave such that combining two bad dynamics yields a good one, much like how alternating two losing games yields winning. Parando's paradox doesn't violate probability laws. It just highlights that expectation values don't add simply when switching contexts. The paradoxical feeling comes from our linear intuition. A real-world analogy might be switching between two bad investment strategies in a way that capitalizes on market conditions differently, somehow yielding profit. In summary, Parando's paradox reminds us that in complex systems, the whole can be more than the sum of parts, even in terms of win-loss outcomes, and that randomness plus pattern can produce unexpected results. 39th Potato Paradox. Statement: you have 100 kilograms of potatoes that are 99% water by weight, so 1% solid matter. They dehydrate until they are 98% water. What is their new weight? Explanation: it sounds like losing 1% water shouldn't change things much, but the answer is startling. 50 kilogram. Initially, 99% of 100 kilograms is water, so water equals 99 kilograms, and dry matter equals 1 kilogram. After drying, the dry matter, 1 kilogram, now constitutes 2% of the weight, because 100% minus 98% water equals 2% solid. Let total new weight. Bar W. 2% of W is 1 kilogram. The non-water hasn't changed. So W equals 1 kilogram divided by 0.02 equals 50 kilograms. The counterintuitive drop from 100 to 50 kilograms is the paradox. The fallacy would be to think water goes from 99% to 98%. That's a change of just 1 percentage point. So maybe weight drops a tiny bit, which is wrong. The correct reasoning is to realize the ratio of water to solid changed significantly. At 99% water, the ratio of water to solid is 99 to 1 equals 99. At 98% water, the ratio is 98 to 2 equals 49. So the water content actually had to drop such that the ratio went from 99 down to 49. In fact, half the weight is lost as water evaporates, because removing water increases the solid percentage non-linearly. The potato paradox teaches a good lesson in percentages. Going from 99% to 98% water content is not a trivial change in absolute water loss. You're doubling the concentration of solids from 1% to 2%, which requires losing a lot of water. Thus, 49 kilograms of water must evaporate, leaving 50 kilograms total. It's often surprising. Many think the answer might be around 99 kilograms or 98 kilograms, but it's much lower. This is a veridical paradox. The result is true, but counterintuitive. The resolution is clear once you do the math step by step with actual quantities. It underscores how our intuition for percentages can fail, especially for extreme values. So, going from extremely water-laden to slightly less extremely water-laden can involve dramatic shifts in total weight. 40th Schwartz Lantern Paradox. Statement: approximating a cylinder with a lantern of flat panels, like a polyhedron inscribed in the cylinder, can make the computed lateral surface area arbitrarily large, even though the cylinder's true area is fixed. Explanation: the Schwartz lantern is a pathological example in calculus. Imagine approximating a circular cylinder by a series of rings of flat panels, like a zigzag surface connecting two circles. One might expect that as the approximation gets finer, more panels, the total area of the panels would approach the actual curved surface area of the cylinder. However, depending on how you refine it, in particular using more rings while also making them slant differently, the total area of the flat facets actually diverges and can become arbitrarily large. This is paradoxical in the sense that it challenges the intuition that a finer approximation yields convergence. The root cause is that the sequence of polyhedra does not converge nicely, not uniformly, to the cylinder's surface. The facets start oscillating rapidly. The effect is that the limit of areas does not equal the area of the limit shape. The Schwartz lantern paradox highlights that for surfaces, unlike for length or volume, the notion of limiting area can be sensitive to how the approximation is done. It's a caution in numerical integration or differential geometry. Simple refinement isn't enough. One needs a well-behaved approximation. The paradox is resolved by realizing it's not a true paradox, but an artifact of taking limits improperly. The cylinder can be approximated in a way that does converge in area, like using finer horizontal bands. But Schwartz's example shows a counterintuitive scenario where the discrete surface wiggles in such a way that area blows up. In essence, the lateral surface area is not a continuous functional under certain limit processes. Thus, the Schwartz lantern paradox demonstrates a counterexample to the naive expectation that polyhedral area approaches smooth area, reminding mathematicians to impose conditions like bounded curvature or convexity to avoid such surprises. 41st Sphere Eversion. Statement: topology says it is possible to turn a sphere inside out through continuous deformations without tearing or creasing the surface, despite seeming impossible to do so in ordinary 3D space. Explanation: sphere reversion means smoothly turning a two-dimensional sphere, surface of a ball, inside out. Intuitively, one would think you can't do this without ripping or forming a sharp crease, since for a circle, trying to turn it inside out causes a loop or cusp. But astonishingly, in 1957, Stephen Smale proved that a sphere can indeed be averted with regular homotopy, allowing the surface to pass through itself. The process requires self-intersections, but it can be done in a way that the sphere remains differentiable and no permanent creases form. The paradoxical part is that most people assume such an inside-out turning is topologically forbidden, like trying to turn a basketball inside out without cutting. However, the key is that the sphere is allowed to intersect itself during the eversion, something physical rubber might resist, but mathematically it's allowed as long as it's not torn or sharply creased. The result is paradoxical because it defies normal geometric intuition. A sphere seems to have two distinct sides, inside versus outside, but under the rules of topology, no constraints on self-intersection, that distinction can be removed. The proof and processes, like Moran's famous sphere eversion, or the later ones visualized in computer animations such as turning the sphere inside out, show explicit constructions. Essentially, parts of the sphere are pushed through others in a symmetrical way. At one point, the sphere looks like a complex, scalloped shape, the halfway model, often a shape called Moran surface. Then it continues until what was originally the inside faces out. The resolution of this paradox is recognizing that inside and outside are topologically meaningless for a surface in 3D if intersections are allowed. The sphere eversion doesn't contradict any theorems. It's actually a consequence of higher-level algebraic topology. The Gauss degree of the normal map is invertible in 3 dimensions, unlike in 2 dimensions where a loop cannot be turned inside out without a cusp. The process is often cited as a classic counterintuitive result in topology, and it shows the difference between topology and common geometry. In summary, yes, you can turn a sphere inside out with no cuts. It's weird, but true, making it a veridical paradox. That initial intuition says no, but mathematics says yes. 42nd staircase paradox. Statement: the length of a diagonal of a square seems to differ depending on how you measure it. If you approximate the diagonal with a staircase, zigzag path of small steps, the length of that path is the sum of horizontal and vertical segments, which always equals the perimeter for any subdivision. For instance, a 1 by 1 square's diagonal is the square root of 2, approximately 1.414. But an arbitrarily fine staircase approximation can have length 2. Explanation: the staircase paradox is essentially about the concept of curve length and how it doesn't behave well under some limit processes. If you take a unit square and approximate the straight diagonal by little right-angle steps, like a path that goes over 1 over n, up 1 over n, over 1 over n, up 1 over n, repeated n times, the path is a polygonal line that stays on the grid. Each small step pair, right then up, has total length 2 over n. Doing n of those gives total length 2 over n equals 2. No matter how fine n is, the length of that jagged path remains. 2. It does not approach the true diagonal length of square root 2. In fact, if you make the staircase steps even more funky, like not aligned at 45 degrees average, you can get a path that approaches the diagonal area-wise, but has length arbitrarily close to 2, or even greater if you let it oscillate. The paradox arises because one might think as the step size tends to zero, the jagged path converges to the diagonal line, so the lengths should converge as well. But they don't, because convergence in shape doesn't guarantee convergence in length. The resolution, the limit of a sequence of curves, can be a different curve whose length is not the limit of the lengths. Length functional is not lower semi-continuous under that mode of convergence. In this case, the polygonal approximations are converging to the diagonal in the sense of pointwise or uniform convergence, but their lengths stubbornly stay at. 2. The mathematical takeaway is similar to the Schwartz lantern number 40. Not all limits commute with measurements. The staircase paradox is essentially why the definition of curve length requires taking the infimum over all such approximations. Among all polygonal approximations of a line segment, the straight one is shortest. Any zigzag is longer. Thus, the length of the segment is the least upper bound of lengths of inscribed polygons, which indeed is. Square root of 2. If one restricts to grid-aligned polygons, then you're not using all possible approximations, so you get a different result. 2. So the paradox teaches that to measure lengths correctly, you must allow approximations that can be oriented optimally. It's a cautionary paradox. The length of a curve is defined by the supremum of lengths of all fitting polygonal chains under refinement, not a specific subset of them. In summary, a crooked path can be much longer than the straight line connecting its endpoints, and even if you straighten it out in the limit, if you constrain the way you approximate it, you might overestimate length. The diagonal's true length is square root 2, but if you insist on measuring it with tiny orthogonal steps, you'll always get 2, illustrating the subtlety in definitions of length. 43rd string, girdling Earth paradox. Statement: imagine a string snugly wrapped around the Earth's equator. Add just 1 meter of length to it and somehow lift it so it's equally above the surface all around. How high off the ground will the string be? Explanation: surprisingly, the string will hover about 16 centimeters above the Earth's surface, roughly 5.3 inches. Regardless of Earth size, this is often counterintuitive. Many expect a very tiny gap, but 16 centimeters is a noticeable gap. The reasoning: the circumference c equals 2 pi r for radius r. If we increase length by delta, L equals 1 meter, the new radius r prime satisfies 2 pi r prime equals 2 pi r plus 1. So r prime minus r equals delta r equals 1 over 2 pi meters. 1 over 2 pi approximately equals 0.159 meters equals 15.9 centimeters. This result doesn't depend on r. The Earth's radius cancels out. So even for a huge radius like Earth, 6,371 kilometers, adding 1 meter yields approximately 16 centimeters gap. People find it paradoxical because adding 1 meter over a 40 million meter circumference seems negligible. Yet because it's spread evenly, the rise is uniform and not so tiny. The scale independence catches folks off guard. It doesn't matter if it's around a basketball or Earth. 1 extra meter gives approximately 16 centimeter gap. The paradox teaches how circumference relates to radius linearly. A small absolute change in circumference results in the same absolute change in radius no matter the original size. There's nothing mysterious. It's just c equals 2 pi r rearranged. But our intuition might think in percentages. 1 meter is an extremely small percentage of Earth's circumference, approximately 0.00000025%. So we expect a proportionally tiny radius change, forgetting that percent of radius change is also approximately 0.00000025%. But Earth's radius is huge, approximately 6.37 times 10 to the power of 6 meters. So 0.00000025% of that, approximately 16 centimeters. So it's consistent. Another way, if you had a loop around any sphere, adding a slack of length L yields slack 2 pi as radial gap. That formula is counterintuitive only if one doesn't realize how division by 2 pi works out. It's a good demonstration of linear versus multiplicative thinking. In summary, the string around Earth paradox shows that even a seemingly negligible length addition produces a surprisingly perceptible gap when distributed evenly. It's a veridical paradox. The math is clear, but intuition often fails. 44th, type-in-type paradox. Statement: in certain type theories, if a type is allowed to be a member of itself, type, one can derive a contradiction akin to Russell's paradox in set theory. Explanation: this paradox is essentially Girard's paradox, or 31, restated in a logical system, say A, programming language or proof assistant. If you permit a type universe to contain itself, you can construct a logical loop. For example, suppose there is a type that is supposed to be the type of all types, including itself. Then one can attempt to form something like the type of all types that do not contain themselves, leading to inconsistency. In more concrete terms, this was seen in early Martin Loeb type theory. Having an type axiom made the system unsound, the resolution, and what modern type theories do is to have a hierarchy of universes, etc. So no type is an element of itself, avoiding the loop. The paradox underscores the necessity of stratification in formal systems to avoid self-reference anomalies. In category theory or certain logical frameworks, this is referred to as the type-in-type issue. For instance, System U by Girard was inconsistent because of it. The paradox is resolved by sacrificing some convenience, no single universe of all types, in exchange for consistency. It's basically Russell's paradox translated into type theory terms. The set of all sets that don't contain themselves becomes the type of all types that don't contain themselves. As in Russell's case, if allowed, you can neither include nor exclude it without contradiction. So, the lesson is, no type system can have a universal type of itself without inconsistency. Girard's paradox proved this. Thus, type theories incorporate a cumulative hierarchy or other mechanisms, like ZF set theory does, to circumvent the paradox. Now, we'll proceed with additional paradoxes across various domains, following the numbering. 45th, vanishing puzzle. Statement: a vanishing or disappearing object puzzle is one where a set of figures, like people or objects, seems to inexplicably reduce or increase in number after a rearrangement of parts. Explanation: this refers generally to puzzles like Sam Lloyd's Get Off the Earth or other dissection illusions, where, say, 12 cartoon characters become 13 after rearrangement of parts of an image, One variant involves an illustrated group of people. Cut the picture into sections and swap them, and one person seems to disappear or appear. How? The trick is similar to the missing square puzzle. The images are drawn such that each person is split, and when reassembled, the fractions of people add up differently. Effectively, one person's worth is distributed among the others. For example, each of 12 drawn figures might be slightly taller or shorter. After rearrangement, you count 13, but each is a bit smaller, hiding the fact that the total person units is still 12. It's a purely perceptual illusion, not a true paradox in logic. The term vanishing puzzle covers any mechanical illusion where moving pieces around produces a count discrepancy. The resolution always lies in careful examination. There is either a hidden overlap or each figure is not identical between arrangements. Some are stretched or compressed, so the count changes. Martin Gardner wrote about these in detail, explaining how our eyes count discrete objects but miss the subtle resizing. In essence, mass or area is conserved but partitioned differently, fooling the count. These puzzles illustrate how our brain's counting heuristic can be foiled by continuous transformations. They are in the same family as the chessboard paradox and missing square, 28 and 36. Indeed, Sam Lloyd's paradoxical dissection of the chessboard is a type of vanishing area puzzle. So, the vanishing puzzle paradoxes are resolved by observing that what we think are identical units, people, squares, etc., before and after, are not actually identical. A little bit of each unit has been relocated to collectively form an extra, or missing unit. It's a delightful demonstration of a falsitical paradox. Our naive count is fooled, but there's no real violation of conservation. 46th. Von Neumann paradox. Statement. In analogy to Banach-Tarski, John von Neumann discussed a paradoxical decomposition in the plane involving the group of rotations, a free group of two generators, often called the paradoxical decomposition of the plane or von Neumann paradox. Explanation. The Banach-Tarski paradox, duplicating a ball in 3 dimensions, has a sort of 2-dimensional counterpart. You cannot get a paradoxical decomposition in the plane using just Euclidean moves if you require the pieces to be measurable sets, because the circle group is solvable. However, if you use the group of area-preserving transformations with 2 or more generators, like 2 independent rotations on the plane that generate a non-abelian free group, you can get a paradoxical decomposition of the plane. The von Neumann paradox typically refers to splitting a disk, minus a point, into pieces that can reassemble via rotations into 2 disks of the same size. It's essentially a 2D version of Banach-Tarski, using F2, the free group, on 2 rotations acting on the plane. The catch is that in the plane with only translations and rotations, which form an abelian group, you cannot do Banach-Tarski, that's a theorem, but with appropriate group actions, like including 1 dilation or an additional constraint break, paradoxes emerge. Von Neumann's work was actually to classify when paradoxical decompositions are possible, introducing the notion of amenable groups versus non-amenable. He identified that the free group, non-abelian, leads to paradox, whereas abelian groups, like R, squared under translation, do not allow that paradox. They are amenable. So, the von Neumann paradox might specifically denote the paradoxical decomposition in 2D under a non-amenable group of motions, like the two-generator rotation scenario. The resolution is the same as Banach-Tarski. It's not a real physical paradox, but a mathematical insight that if you allow choosing non-measurable sets, you can get duplicative decompositions. It underscores the idea of amenability. Von Neumann conjectured, and later it was proved, that if a group is amenable, roughly has an averaging invariant mean, paradoxes don't happen. If it's non-amenable, paradoxes like Banach-Tarski do happen. The Euclidean plane under Euclidean motions is amenable, hence no paradoxical cut and paste. But if you include, say, a rotation of an irrational angle around the origin, and also allow that as a group action inside the disk, you effectively get a free group action on the disk and can do a Banach-Tarski style partition. In summary, the von Neumann paradox refers to a Banach-Tarski type duplication in a two-dimensional setting by using a clever choice of group actions, non-amenable group. It's resolved, or rather explained, by advanced group theory and measure theory. The paradox arises only when using non-measurable sets and non-amenable group actions, so no contradiction in standard measure-constrained geometry. The list continues into probability and statistics paradoxes. These were partially covered in items 101 through 118 earlier. We will ensure none are missed. 47th Birthday Paradox. Statement. In a group of people, how many are needed so that there's a 50-50 chance at least two share a birthday? Explanation. The answer, only 23 people, is paradoxical to many. Intuition might suggest you need a lot more than 23 for a coin flip chance of a match, since 23 is much smaller than 365 days. The resolution lies in combinatorics. With 23 people, there are 23 equals 253 possible pairs of people. Each pair has about a 0.27% chance of matching, 1 out of 365. 253 such pairs make overall probability approximately 50%. The paradox is our surprise at how quickly pair counts grow with group size. By 23, the probability of at least one match is approximately 50.7%. At 30 people, it's about 70%, and at 57 people, it's over 99%. The key insight: it's not one person's chance of matching someone else. It's any pair. We are bad at appreciating how those pair opportunities accumulate. So the birthday paradox is really a demonstration of probability for combinations. It's called a paradox because many people guess a much higher number is needed, but it's a veridical result. Nothing contradictory, just counterintuitive. The math. Probability. All 23 have different birthdays. Taught 365 over 365. 364 over 365. 365 minus 22 divided by 365 is approximately 0.492. Hence, 1 minus that is approximately 0.508 chance of some match. It's interesting to note that at just 23, that flips over 50%. The paradox teaches caution in reasoning about probabilities in larger sets. Direct intuition often neglects the combinatorial explosion of comparisons. 48th Monty Hall Problem. Statement. On a game show, you face 3 doors. Behind one is a car, prize. Behind the other 2 are goats, nothing. You pick one door, but it's not opened yet. The host, who knows what's behind doors, then opens one of the other two doors, revealing a goat. You are then offered a choice. Stick with your originally chosen door, or switch to the remaining unopened door. What gives a better chance to win the car? Explanation. Switching doubles your chance of winning. You'll win 2/3 of the time by switching versus 1/3 by staying. This result famously perplexes many, even some mathematicians at first, because a lot of people reason it's 50-50 once one door is opened. The crux, your initial pick had a 1/3 chance of being correct. That means there's a 2/3 chance the car is behind one of the other two doors. The host's action of opening a goat door doesn't change that initial probability. It just condenses the 2/3 probability onto the single remaining unopened door. By switching, you capitalize on that 2/3 probability. Another viewpoint. If you picked wrong initially, which happens 2/3 of the time, switching will correct that and win. If you picked right initially, 1/3 chance, switching loses. So indeed, 2/3 versus 1/3. The paradox is psychological. Many feel that after the reveal, there are two doors left, so equal chances. The resolution is conditional probability. The host's choice is not random. It's informed and contingent on your initial pick. That information affects the odds. Once explained properly or simulated, it's clear switching outperforms staying. The Monty Hall problem is a classic demonstration of how our intuitions about probability can go astray, especially regarding conditional probability and information. It's now widely used to teach careful, probabilistic thinking. The correct 2/3 versus 1/3 solution is well established, yet it remains one of the most paradoxically phrased puzzles because it goes against gut feeling. 49th, Gambler's Fallacy. Statement: in a fair coin toss or roulette, etc., after a long run of heads in a row, many gamblers believe tails is due and thus more likely on the next toss. Explanation: the gambler's fallacy is not a true paradox, but a common logical error, the idea that chance has a memory. In reality, each coin toss is independent. The probability of tails remains 50% every time. There is no self-correcting mechanism in random independent events. The paradoxical aspect is psychological. People expect short-term sequences to reflect the overall probabilities, the law of small numbers. If they see a streak of heads, they think a tails must come to balance things. This is wrong. The probability of a tail after, say, 6 heads in a row is still 0.5. Gamblers fallaciously treat streaks as making the opposite outcome more likely. The correction is understanding statistical independence and the concept that randomness is memoryless for independent events. Another angle. In a long series, deviations will tend to even out proportionally, but that doesn't force an immediate reversal. For example, if you toss a coin 1,000 times, you expect about 500 heads, but if you got the first 6 all heads, you still expect roughly 500 heads in total out of 1,000, meaning over the next 994 tosses you'd expect about 494 heads versus 500 tails, slightly skewed towards tails to average out. But on any given next toss, it's still 50-50. The gambler's fallacy is paradoxical to some because of a mistaken notion of self-correction in random processes. It's resolved by carefully distinguishing between long-run expectations and short-run probabilities. Knowing that a fair process has no memory resolves the paradox. A coin doesn't care what happened before. The fallacy has caused many gamblers to make bad bets, thinking the odds shift in their favor after unusual streaks. It's an example of our brains finding patterns and causality where none exists in purely random sequences. 50. Simpson's paradox. Statement: a trend or advantage that appears in separate groups of data can reverse when the groups are combined. In other words, one treatment can have better success rates in each of two subgroups. Yet overall, it has a worse success rate when the subgroups are pooled. Explanation: Simpson's paradox is a statistical phenomenon where aggregation masks or reverses. Relationships, a classic example. Suppose in a medical trial, treatment A has a higher recovery rate than treatment B for both men and women considered separately. However, when you combine men and women, treatment B shows a higher overall recovery rate than A. How can that be? The resolution usually lies in confounding factors and different group sizes or base rates. For instance, maybe treatment A was given disproportionately to more severe cases, or one gender had a different weight in totals. In the famous hypothetical, treatment A might have been given to many very sick patients, who often died, regardless, whereas treatment B was given to milder cases. Within each severity category, A was better, but overall, B treated more easy cases, boosting its aggregate success. Simpson's paradox teaches us that ratios and percentages can't be blindly combined. We must account for lurking variables. It's not a logical contradiction. It's a caution that aggregate data can mislead. The paradox often surprises because people expect if A is greater than B in Group 1 and A is greater than B in Group 2, then A is greater than B overall. Simpson shows not necessarily if the group proportions differ. A concrete numeric example. In a university admission, Department X and Y both admit a higher percentage of women than men, but total admissions show women's overall admission rate is lower, possibly because women applied more to a very competitive department. The paradox underscores the importance of stratifying data and the potential for confounding. The resolution is to realize percentages must be weighted by group sizes, and the weights can cause reversals if correlated with success rates. Simpson's paradox is quite common in real data. The paradox is that our intuitive transitivity of inequalities doesn't hold for ratio measures across combined groups. Once explained, it's logical. The base rates matter. It's a good reminder. Always check if aggregated data hides subgroup trends.